In this video we will continue on with our discussion of forces, but instead of classifying these forces in terms of the fundamental nature of the force like physicists do, and they're trying to understand what is force and matter, we're going to look at it in terms of what's best in order to find our free body diagram and to solve Newton's second law. And in this field of mechanics, there are certain forces that show up in every problem, and we are able to find them with an acronym, and the acronym we're going to use is WANT the force, or WANTf. This stands for the different type of forces we can see: weight, normal, tension, friction, and applied. Applied forces are very varied, include springs, electric fields, magnetic forces. We'll come back and talk about those forces later on. Primarily, in this video, we'll talk about W, N, T, and F. W stands for weight. On the Earth, a body's weight is the gravitational pull of the Earth upon the body. Now, we often say that Johnny's weight is, for instance, 200 newtons or 30 pounds. You have to be kind of careful about that. First of all, the weight doesn't belong to Johnny. If there was no Earth, Johnny would have no weight. So the weight, like any force, is actually an interaction between two objects, not just one. You can't have a force that just appears out of nothing. The force has to have a cause. It has to have an object. And we'll come back to this. This leads us to a discussion of what's called Newton's third law. So there has to be that. That's one thing. So when you're in outer space, you have reduced weight, but you still have weight due to the Earth. All right. So gravity is interesting. Pulls everywhere. Also, it's a vector. You should say that the Johnny Earth weight is 200 pounds down toward the Earth. And we don't usually do that in everyday language, but that's wrong. It's a vector and needs a direction. So the direction here is toward the center of the Earth. And the magnitude, at least if you're close enough to the planet Earth where the Earth you cannot see its curvature, can be found with the formula mg. This is the mass, and this is the acceleration, 9.8 meters per second squared, that we found earlier with free fall. Okay, so we got a formula, we have a direction. If you start this, the object has a pull from what's called the center of gravity. We'll just consider it to be the center of the object. You draw the arrow down toward the Earth, and it's going to have an arrow length of this amount. That's weight. The next force that you usually find in these problems is what's called the normal force, and that's because you probably have two objects that are touching each other. So the normal force, it's not like psychology. It doesn't mean normal as compared to unnormal. Normal actually means perpendicular. It's the mathematical definition of normal. This is a force of contact. So unless you have two surfaces touching, you don't have this. It's a force of contact between two surfaces. The force is always perpendicular to the surface of contact. So let's say you had some object and you had like this, and I'm not drawing a free body diagram, I'm just showing you that there will be a normal force on that block, and it'll be at a right angle. By the third law, we also know actually, or we'll talk about later in videos, that there's actually a force down like this on the whatever this is, table or what have you, pushing in the opposite direction, and it will also be at a right angle to the surface of contact. If you happen to have something like this, and there's an object setting here, then there will be a force of contact, and it will be like that. And likewise, by the third law, this, whatever it is, will have a force like that, and it will be at a right angle, and this will be at a right angle. They're always at a right angle to the interface between the two items. Now, the only thing else I can say about the direction, besides it's perpendicular, is it's such that the force is trying to push apart these things. So the reason I know that this red arrow is pointing up is that this table is attempting to push that block away from it. And likewise, this table is being pushed away by this block. This is because of the fact that they have these electrons, and electrons, we find out later in physics, are like charges. Maybe you've heard that in chemistry. They're all negative. And like charges don't like each other, and they tend to repel. So this is a case where they're not chemically binding. They're actually feeling this repulsive force because of their charge, and it's pushing them apart. If you don't know anything about electrons and the charge and so forth, that's all right. You don't need to at this point. You just need to know that these arrows push in such a way as to try to separate the two objects, not suck them together. Big important point here about these guys. There is no formula like W equal mg. So I can't say N is equal to something. There is no such general equation for finding the magnitude of the normal force. You have to solve Newton's law to do this. No general equation. All right. Now, a lot of students will make a mistake and say, hey, the normal force is equal to mg. In some cases it is, in some cases it is not. All right. So just making that assumption is you're just taking your grade in your own hands, potentially to get seriously hurt. So no such equation. You got to solve Newton 2 to find the normal force. Tension. There's often a case where there are strings in a problem. If there are strings in a problem, or if you have a cable upon the object, we say that there's a force involved, and that force is a tension force. Now, cables are different than rods. If you attach two objects with a rod, you can push inward on both sides of these two masses, and the rod will push back in the opposite way. But if you have a rope, and you apply a push in like this, and this is a rope, then the rope will just sag, and it will not apply a force, and the two blocks will fly in. So whether you have a rod or a rope actually makes a difference. Engineers, for instance, have to be concerned with this. If they know these things are going to get pushed in and they don't want them to move, they have to use a steel rod. They can't use a cable. Cables can't push. Now, how does that work out in terms of math? What you usually do is you solve the problem, and if you find that the force in this rope was going this way, that it had to push like this, you know that it can't push, you cut the rope and then resolve the problem. And that's how you make the problem work. If you have a rod, it can push outward and you're okay. Alright, if you don't again totally follow that, I think it'll be a lot clearer once you do a lot of examples. Another thing that can show up in is F. F is friction. Friction is an incredibly complicated subject. There are, in fact, many parts of friction and different types that we have no formulas whatsoever to work. And if tire companies spend billions of dollars, as does ball bearing companies and others, either trying to reduce friction, in the case of ball bearing companies, or increase friction, as in the case of tire companies. So friction can be good or bad. It's whether you want it there or not, and whether you have too much or too little. We're going to limit ourselves to just sliding friction in our case. And we'll come back and talk about how we get formulas for that, because it's such a big topic, in a separate video. What I do want to say is that in order to have this sliding friction, you're going to have a surface of contact. And if that sounds like, hey, we heard that about the normal force, guess what? There's actually a connection between those two, between the normal force and the friction force. The applied force. The applied force is everything else in a physics problem that you didn't have because of one of the others. Most common thing is to have something like this. Maybe you got a block and you have Johnny here, and it says Johnny pushes with a force of, say, 5 newtons up this incline. Then Johnny would have a little arrow that relates to Johnny, and he would be an applied force. Another example of applied forces in this course is you have these things called springs. And that spring may be a pull to a block. If you stretch that block, that string will pull back. If you push in on that spring, it'll push back on you. Hopefully you played with springs sometime in your life. Short thing of it is weight, applied, normal, tension, friction. There's no V. There's no such thing as velocity in my forces. There's no such thing as little a. I'm looking for forces. There's no C, as in a special force called the centripetal force. Centripetal force must be one of these forces that I've already labeled. So we're going to use this in the free body diagram to find all the forces in the problem and add them up. Alright, that finishes this discussion of the video, and we'll move on to talking about how we're going to use this to solve Newton's second law.